right, why don't we go ahead and get started? Looks like we've got a good group here in the Zoom room. So we will go ahead. We've got a lot to cover today about R. So we'll jump right in. Before we get started, I just want to have there's my contact information. So my name is Victoria Crystal. I'm an adjunct professor at the University of Nebraska, Omaha, and I teach geology. So I'm a geologist and a paleontologist. And you'll see some of my examples of data come from some of the work I do with fossils. And this cat right here, this is Horace. He might meow a little bit, but he loves to sit in the office here with me. And if I close the office door and try and lock him out, he meows and he scratches at the door. So it's a lot less distracting to have him sitting here than to have a constant noise from the door. So my contact info, my email address is right there. I've also worked at the University of Colorado. So I have that email address because it's a little bit easier to remember. It's just victoria.crystal@colorado.edu. That's just my email address there, name plus Colorado. And so today I'm going to be talking to you all about data visualization with R. So here's a little roadmap of what we're going to be talking about today. So first, we're going to start off with what is R. Some people might have heard of R, some people might not have heard of R. So we're just going to give a basic overview of what R is and what it can do. And then I'm also going to talk about RStudio. So I use both of these programs together, R and RStudio. And RStudio just provides a much better interface, I think, for doing analyses and data visualization. So I'm going to talk more about how I use those together. Then I'll go over the basic interface and the components that you see when you open up these programs. And then we'll get to the basics of code, writing code in R. We'll talk about loading packages, some simple statistical analyses, and then we'll get to kind of the best part is making graphs, charts, and plots. And then I have an example here that is all about flattening the COVID-19 curve. So R is really, really great for modeling data. And one of the great types of data that you can model with R is epidemiology data. And so there's a lot of different packages that are all about modeling viruses spreading throughout the community and throughout the world. And so we're going to give an example of how we can use that modeling in R using some COVID-19 models. None of these models have real data. It's all just hypothetical modeling about how the disease spreads from person to person in the community. And I'm also going to talk a little bit more about what a mathematical model is and what we use to make one. And then I've got some resources here to help you if you get stuck or have more questions about R. And all of this material that we go over today is going to be emailed out to you after this. There's a question in the Q&A. You don't need to install R. If you'd like to kind of follow along, you can download both R and RStudio, but you don't have to at all. Mostly this webinar is just going to be informative, kind of giving you the important information about it. And so you can definitely download it at a later time and use all the information from today later whenever you need to use R or install it. All right, so let's go ahead and jump in. So what is R? I've already talked about R a lot. So R is a programming language and open source software that's used for a lot of different data-driven purposes. So primarily data manipulation, statistical analyses, and then graphical display. Those are kind of the three main things that R is used for. But of course, modeling, like we will talk about the model later on. And so lots and lots of different purposes. And so right here, I've got a link to a really cool gallery that shows all of the different types of data visualization that you can do with R. So the package that we're going to use to do all of our data visualization is ggplot. And I'll talk more about what a package is and what ggplot does. But this is just a really cool site that kind of shows all of the different types of plots that you can make with ggplot. So you can make some scatter plots. You can annotate your plots, adding lines or other axes. You can make these cool marginal plots. You can customize the appearance, change the background. I'm going to keep scrolling down until we get to the really cool stuff. You can make some box plots or stem and whisker plots, whatever it is that you call these. You can make histograms. You can make some facet grids, and I'll show you how to do how to spread things out in a grid like this. Just lots of cool themes and colors for your data. Lots of different colors, lots of interactions. So you can make an interactive plot where when you hover over the data, you get these little pop-up information about what that data point represents. You can also make some really interesting, intricate plots. But let's get down here. You can make art. So you can program R to make art and code different awesome designs and shapes. But then here is some of the coolest. You can actually make these interactive plots, or excuse me, animated plots, where you have, you know, an XY grid, and then you can have time component where you animate it to show as time progresses. So this is our animated bubble chart. We can have animated grids. So just a lot of really wonderful options. I could do a whole webinar just on this website, but I won't. I'll give you the rest of the information, but that link will be sent out with these slides for you to use. So the other great thing about R is that it's extendable. So it comes with a lot of the basic codes that are already programmed into it. But what you can do is you can download these additional packages, or you can develop these additional packages, which is each a unique set of commands that R will recognize that when you input that command, it is basically that you are telling R to do a specific thing. And so you can make a package to do anything. There's a lot of packages that we'll take a look at today that's going through how to make these different plots. So like that ggplot is a package to make really nice looking graphs, but you can insert or develop packages to do anything you want. If you want a command that will send an email to yourself, you know, you want to email whatever is in the input, you can do that. If you want to create art, like we saw in that ggplot, there's packages, separate packages for that. We're going to talk about a separate package that models virus transmission through a population. So it's just a different set of commands that you can just add into R, aside from the ones that R already knows. Another great thing about R is that it's easily integrated with C and C++ and Fortran, which I personally don't use that often, but I know some of my colleagues really like that it can be integrated in this way. And then finally, you can also output some documents. So you can output all of your code and anything that you generate through that code in different documents and different forms. So it can be HTML, PDF, Word, and I'll show you how to do that. All right, and then we've got RStudio, which is basically this integrated development environment for R. It basically just makes working with R a lot easier kind of visually and more organized. So it has this console that's, where's my mouse here? Does anyone see? There it is. That's pictured down here. And then we've got this really nice organized workspace layout that we're going to take a look at once we pop into RStudio. There's a lot of nice syntax highlighting tools that come with RStudio, nice tools for exporting plots and files. You can really easily just save a plot that you generate as a PDF or as a JPEG without having to download it or write a code. A big long code. It's really just one command that allows you to save it. And then you get this really nice organized R Markdown document that has all of the capabilities of a word processor along with all of your code. And I'll show you that in the next couple slides. And RStudio is available both for either desktop or on your web browser, whichever you prefer. Before we get too far into this, I do want to warn you, just like any other learning curve, any other coding language, there is a huge learning curve here. It's really tough to learn a new coding language, just like it is to learn a new spoken language. It's challenging. There's a lot of commands, you know, there's a lot of words, there's a lot of terminology, and it can be a little bit frustrating, especially if you've never done it, if you've never learned a coding language before. So just be aware, it's going to be a little frustrating. It's going to be a steep learning curve, but once you start getting the hang of it, it really opens up and gets a lot easier. So bear with me if some of this seems complicated. It'll be it'll be a little challenging the first couple times you think about it, but once you get it, and it's easy. Or I shouldn't say easy, it's less challenging. So with that, let's bear forward and learn about R. So this is the interface that you get for just R by itself. So if you download, if you go to the link that I put in the description of the webinar, it shows you where to download R. So you can just download R, and this is what you get when you open it. It's just kind of this big area. There's no real organization to it. And so I actually never do anything just in this R interface. I always use RStudio. And RStudio needs to have R installed on the computer to run it, but you can just open up RStudio. You don't have to have both R and RStudio open, because RStudio will pull directly from the program associated with R. So this is the RStudio interface. It's got all of these different boxes on it, so you can have a lot of different things going on at once, whereas in R, it would just be a steady stream of things right here and not a lot of opportunity to see what data you have open or to see a plot that you create at the same time. So this box right here, the kind of top left box, is the bread and butter of RStudio. So this is what's known as the R Markdown window. And an R Markdown is a document. It's a really nicely organized document that has all of your work. So you can have your code, any plots that you make, any text that you generate, any tables you make, all of it's going to be there in this R Markdown. And it has the capabilities of a word processing document and writing your R code and commands all right in here. So a lot of times I have to generate reports based on my data. And so instead of going back and forth between R and my Word document that I'm writing the report in and then like tying it back and then copy pasting and all of that, I do everything in R Markdown now. So I have all of my word processing capabilities here. There's different syntax to tell R Markdown or to tell RStudio that you want a title or you want something bold or you want something italics. But it has all of those capabilities. You just have to put it in the code, in the syntax. And then it has your code written right there and then any outputs. And it's a really, really nice organized file. You can write your whole report in there, format it there. You don't really have to do anything else. No copy pasting from program to program. The other parts of the RStudio interface, down here we have the console window. And so this is where it's actually showing the progress of your code being run. And really, I just use this because it'll show you warning messages or anything that goes wrong. It'll show you error messages in there. Then we've got the environment and history window. So this shows you what variables you've programmed, what data sets you have open, what data sets you've written. Anything that you create is going to show up here. And I'll show you how this works as we go on and explore. And then finally, you've got your viewer window. So this is down here where you're going to view all of your plots. You're going to view what packages you have installed, any files you have, and it's also where there's a really nice help function, and it'll show your help function down there. All right, so why don't we open RStudio and start exploring, and then we'll come back to the PowerPoint slides in a little bit. So I've got RStudio open right here. So this is the RStudio for desktop. So this is what the desktop version looks like. The first thing that you're going to see when you open it, so I already have everything all set to go in here for the class, but when you open it for the first time, it's going to ask you to create a project. So you're going to get a window that actually looks something, hang on, I actually don't want to close it all out, but it'll just say new project, and then it's going to show you actually, hang on, why don't we just do this? Let's click here and we'll try that again. I just want to open a new one. There we go. That's what I wanted. So it's going to show you here, create project. And by directory here, it gives you these options, new, existing. It just means folder. So new directory is a new folder, an existing directory is an existing folder. So you would just click that and then you can tell it to open or browse wherever you'd like. So I'm not going to do that to keep this open. And then once you open that project, you're going to have to open a new R Markdown file. So you go up here, back to File, New File, and then you want R Markdown. And again, I'm not going to click it because I've already got it all ready to go, but that's how you do your R Markdown. And then at the top here, you're going to see something that says output. And I have it set right now to PDF and HTML, but that's just what the output of your R Markdown is going to be. So let me show you an example of an R Markdown. So this is the R Markdown that's associated with this R Markdown file that I've created. So this is just the HTML export. You can see .html up there. And so this shows a little bit about what that report would look like. So you can do your headings, you can do bold, you can have text as normal in a word processor. That's my regular text. And then anytime that you have code, it's going to show up in a gray box, and the output that is generated from that code is going to show up directly below it in a white box. And so you can also, this is a table that we're going to make in a little while. Scrolling down, it's a lot of data here. It'll also eventually show all of the plots that you make. It'll be right there in the document. And so this is where it comes in handy for a word processor. You can have paragraphs and paragraphs of text, and then you can have your graph and then more text talking about it. So this is what it looks like, and this will be sent out to you at the end of the webinar. So you'll get a copy of this. So let's get to it. Oh wait, real quick, before we get to it, I need to show you how to generate that R Markdown file. You just go up here to where it says knit, select the dropdown, and then you can knit to HTML, PDF, or Word. And so that's just going to generate this file that has everything that you've put in your R Markdown. So that's how you generate it. The way that you make those headers, like we saw at the top of the page where it said our webinar with DoSpace, is you have to tell it that this is separate from regular text. And the way that you do that is you use this syntax of putting what we now call hashtags in front. So one hashtag means this is a heading. 2 hashtags means this is a subheading. 3 hashtags would mean a subheading, and you can add as many hashtags as you want to create headings and subheadings, etc. Regular text is just typing regular in there. So, I typed this is our R Markdown. And then whenever you put code, so whenever there is a code that you want to run, you put it in this gray box, which is known as a code chunk. And this is one of the great things about RStudio, is that it separates out your code very clearly from the rest of your text. And to do that, you just go up to here where it says insert, click the drop-down menu, and then select R. And you can, put code in any of these languages if you use them. I only really ever use R, but I have colleagues who do Python occasionally or SQL, and you can just insert a code chunk in that language. And that's just really specifying to R that the codes are going to be written in this specific coding language. So if you select an R chunk, it's going to recognize that these are R codes. If you select a Python chunk, it's going to recognize that it's a Python code. And the way that you can tell what code it is at the top of your code chunk is going to be a little curly bracket, and it'll say R. You can also add something. So when it first shows up, here I'll show you what it looks like. It just has R, but then you can add whatever the title of this code chunk is. So this is the first one or something like that. You can call it whatever you want. And that's just telling it this is a code chunk in R. And the thing that denotes this code chunk from just the regular text are these 3 little apostrophes at the top and bottom. And that's what's telling R, as it's reading this entire document, it reads hashtag as a heading. It reads 2 hashtags as a subheading. It reads just typing as regular text. And then when it sees these 3, it recognizes that as the start of a code chunk, and then the 3 again as the end of a code chunk. And so as it goes through, it'll recognize that only within that box are commands that it needs to do something for. And that is actually the apostrophe that's next to the 1 with the tilde on it, not the regular apostrophe. All right, so let's get to the basics of coding. So I have gone ahead and just created a bunch of code chunks that have different codes that we're going to work on today. So built into R is simple arithmetic. And so, for example, here in our first code chunk, which I've written out, this is our first code chunk, and I've denoted that as the title. If you just do any sort of simple arithmetic, like 2 plus 3, R is going to know how to do that automatically, sort of like a calculator, or 2 times 4, whatever it is. The little asterisk is going to be the times symbol. R is going to recognize that. And so to run these commands, you can either click this little play button to run all of the commands in this chunk, or you can just select what you want to run and then do command enter. And so as you can see, I just selected this, and then below the code chunk is where you get the output of that code. And so there we have the output of 5, right? 2 plus 3, R knows how to do that, it's 5. Same with multiplication, if we want to run that, boom, there we go. It knows simple things like square root, so you just do the command sqrt, which means square root, and then inside of the parentheses, you put the number that you want it to take the square root of, run that, and there's your answer. It also knows simple commands like round. So if you want to round a number, you do round as your command, and then you inside the parentheses, you would put the number that you want to round, comma, the number of digits. So digits equals however many, in this case, 3. So if we go ahead and run that, we see our answer, pi, is rounded there to 3 digits. And if you need more information about what to input for a code, you just hover your mouse over it. All right, right now it's not working. All right, let's click out of the code here and then just hover over it. I don't know why it's not working. Usually it does. Let's try. There we go. So like down here, when I've scrolled down, you see that little box that's appearing. So the command there is class, parentheses, and then the input would be X. So it would be a value. All right, let's see if it's going to work up here again. There we go. So round, input. So what you input in the parentheses is X is your value, comma, digits equals the number of digits. And then you can also do mean. So it recognizes some of these simple statistical commands. So if you want the mean of something, the average, you would just do mean. And then in there, in that parentheses, you can see it says X. So you just input the value that you need the mean of. If you have a whole data set, you need to make sure that you are telling R to consider it as a set together. And so you use this little C command. So C is combine. And so it's basically just saying combine whatever is in these parentheses to be a set. So you don't want to take the mean of just one. You want to take the mean of 1, 2, 3, 4, however many numbers you want. And so that's telling R, take the mean of this combined set of numbers, view it as a data set, and then give me the mean. And so if we go ahead and run that, there we go. We've got the mean of 1, 2, 3, and 4. All right, so now we're going to talk about naming objects, variables, lists, and data frames. So let's go back here to our slides. So creating an object or a variable is basically just assigning a value to a word or a set of letters. So for example, you could assign object to equal 1, or very commonly X is a variable, X equals 2, X equals 5. Anything like that is assigning a variable or assigning an object. And I'll use object and variable interchangeably because it's just kind of one thing, an object or a variable. And then a vector is a list of values. So basically a vector is just assigning a list to a name, a set of letters or a symbol. So you can assign the term vector to mean 1, 2, 3, 4, however many items you want in that list. So you could do X equals 1, 2, 3, 4, X equals 2, 4, 6, 8, whatever you want that list to be. And then finally, data frame. So assigning a data frame or a data table is basically just saying I have this set of data that has a certain number of columns and a certain number of rows, and I'm assigning that a name. So instead of having to type out this data and create this data table every time you want to deal with that data, you just give it a name. And so then you can type data frame. And anytime you type data frame, R is going to recognize that you mean this table. Just like anytime you type vector, R will recognize that you mean 1, 2, 3, 4. So instead of having to type that out every time, you just type vector. So let's actually see how to do that here in R. So instead of using the equal sign, because we use equal signs in the syntax of some of our commands, like up here when we wanted it to round to 3 digits, we did digits equals 3. So when we're assigning an object or a vector or a data frame, we are going to use this less than symbol and a hyphen. So that's the less than symbol that is above the comma. So shift comma. At least that's on an American keyboard. It might be different for those of you that are tuning in internationally. And then you would just do that, the symbol, less than symbol, and a hyphen. And so this is basically just telling R that whenever we type X, we mean 2. X equals 2. So if we run that, I'm going to go ahead and run that. And then you see up here in our environment that we now have a value that X equals 2. So if we forget, what did we make X equal? You just look up here in the top right corner and there we go. It's X equals 2. And then if you want to run that, if you want to show X, if you want to run a command that shows X, you just have to type it and then run that. And our output down here is going to show X. It's going to show it as 2. And then all of these commands are showing up in the console because this is where it actually kind of does the running. So when we run something that's complicated, you'll see each step is showing up as being run in the console. All right, so let's do a new object. Once we name X, we can also use that in equations. So we can name a new object as X times 3. So if we name that, we can run that code. And then up here, we see our new object equals 6 because X is 2. We're multiplying it by 3. So it's showing up as X equals 6. And then here is a list or a vector. So let's, for example, we'll do temperatures. So we can list the temperatures from yesterday, today, and the day before. And again, we want to look at this as a set, as a combined set and not individual values. And so we will use this C command and we will name our list as temperatures equals this number of temperatures. And then as we can see up here, it shows up as temperatures and it equals this set. And this 1 to 3 is basically just saying there's 1 row and 3 columns. So if we were to make a table, this would be just a table with 1 row and 3 columns. And it says num because it's numerical data. We can also do this with non-numerical data. So weathers, we can say that it's cloudy, sunny, and rainy. And we go ahead and run that. And it shows up here, weathers is character data, 1 row, 3 columns, cloudy, sunny, rainy. And anytime you want R to recognize something as text or as a word and not as a named object or a name for a list or something, you'd put it in quotes. So we are naming, this list as weathers. And so we are saying that to R, weathers equals something else. But if we just want to type the word weathers in a code, like we want something to be a character datum as a word, you'd put it in quotes. So that's why we put cloudy, sunny, and rainy. Those aren't commands, those aren't objects. That is just a piece of character data that is a word. It's cloudy. Let's say we've got all these lists and we forget how long they are. So we can always do the command length and then the name of the list. And when we run that, it's going to tell us how many objects are in that list. So we ran length of weathers and we've got 3. Now let's say we forget if weathers is character data or if it's numerical data. We can always look up here, or we can run the command class. And if we run class of weathers, weathers being the input in parentheses, it's going to tell us that it is character data. So it's not numbers, it's characters, it's words. We can also add to it. So let's say the next day it was snowy, and so we wanted to add that to our weathers list. We would just rename weathers. And so we would say weathers, again, less than and hyphen to be equals. And then again, combine, because we want to combine it all as one list. Our new value of snowy plus the original weathers. And so if now we rerun this code for weathers, stop meowing. Up here, we can see we now have 1 row and 4 columns because we have added snowy. All right, and then let's say we want to find the mean of our numerical data. So we can go ahead and run mean of temperatures, and there we go. The output is the mean. And then we can also, this is, we don't need 33333. So we can also embed this in round the mean of temperatures to digits equals 2. And one of the nice things about RStudio, you saw it kind of prompted me there. It'll prompt you, it'll help you so you don't have to type out every command in every code. And as you can see, there's also a red X that's showing up here. Ooh, I don't know why that's inverted. Why is that inverting? I've never seen it do that before. That's very strange. But there's a little red X there. And that X is saying that there is something wrong with the code, that if I try to run that, it's not going to run. And in this case, the problem is that we need a parentheses on the end to enclose that command for round. So I'm going to put that parentheses, our error message disappears. I'm going to run this, and there we go. We've got our rounded mean of temperatures. And real quick, I'm going to pop back over to our slides. Error messages. All right, so it is very, very common to get error messages. Actually, why don't I'll just show you what it'll look like if I run that without correcting that error. So I will run that here, and why is it not? Usually we get a big error message down here. Maybe it just didn't. There we go. So now we've got an error message that is showing up as our output. And right now it's saying unexpected symbol in this. And that's because we haven't closed the parenthesis on round. And so it's saying that within this command that we're trying to type, there's a lot of unexpected symbols because we haven't told it that the input for that command is within these parentheses. And so it thinks, the cat just jumped on top of the book. And so it thinks that there's a lot of things that it's not recognizing as an input. So that's why it's saying unexpected symbol. And then you can see once I type that and run it again, it works just fine. So anytime you have an error message, first thing to do is check your syntax. Are all the parentheses closed? Are there any typos? Did you accidentally spell mean wrong? Did you write M-A-E-N instead of M-E-A-N? Are there typos? Is something capitalized or not capitalized that needs to be? Oftentimes that comes into play when you name things because capitalization is important in the name. It has to be the exact name that you type. So capitalization matters. Did you miss any plus signs? So were you adding something? And this will be important once we start making our data or our graphs. Check the inputs for the commands too. Is there something that you need to specify that you didn't? Like if we just tried to hit round, and then a number without saying digits equals, it probably wouldn't work because we need to specify how many digits we need it to round to. And then if that still doesn't fix the problem, all of these things, Google the error message. The really wonderful thing about R being open source is that hundreds of thousands of millions of people are using R. And so if you're getting an error message, someone else has probably gotten that error message too. And there's probably someone out there on the internet who has written out a solution to how to fix the problem. So Google your error message, 9.9 times out of 10, you're going to get the answer on Google. All right, but now let's get back to it. So we're going to start moving a little bit more quickly through some of the code just so we have time to cover everything we need to cover. So this is an example of naming a data set. So there is a built-in set in R called faithful. And so anytime you type faithful, it's going to show that data set. So I'm just going to go ahead and type faithful. There we go, handy dandy. And then I'm going to run this command and we are going to see this data pop up. So this is data from Old Faithful Geyser in Yellowstone National Park. And it has the time of the eruptions of the geyser. So this is time in minutes of the eruption length. And then this is waiting between eruptions. So this eruption on the first line was 3.6 minutes long, and it was 79 minutes of waiting before the next eruption. And so we're going to go ahead and we're going to give this a new name. We're going to call it data because it's way too hard to type faithful every time. Let's only type 4 letters. Let's type data. So we're going to run that, and then you see data appears up here in our environment as data. There's 272 observations of 2 variables in there. So if you want to see that data table, what you can do is you can just type data and run that, or you could type faithful like we just did, or you could type print data and run that. So print means it's going to show it all in the output. Head data means just the first 6 lines of your data set. So if you just want to see the beginning of it. But this is where things get complicated because this is a data set. This is not just a list of variables or a list of numbers, it's a data set. So if we try to take the mean, it's not going to like that. It's going to say this argument is not numerical or logical because you can't take the mean of an entire data set, right? Why would we take the mean of 2 variables at the same time? Doesn't make sense. And so this is where a lot of the cool data manipulation tools of R come in. So here we can load these packages that are all written with a lot of codes for data manipulation. And so these packages, this is the name of the package, dplyr, tidyr, and this one, too long to say all the letters, we call it magrittr. And so to install packages, you go up here to Tools, Install Packages, and then you're going to type the name. So let's say we want to do tidyr. You type the name, select it, and then you'll hit install. I'm not going to do that right now because I've already got it installed and it gets messed up if you try and install something twice. Then once you've got those packages installed, we have to tell R that we're going to use commands from these packages. And so you do that by doing this command library. So basically saying, hey, go into your library of packages, load all the commands from tidyr or dplyr because we're going to need them. So I'm going to go ahead and run this code chunk that loads the library from all of these. You'll get a message that says it's attaching the package. There's a couple objects that aren't loading because I haven't updated the package in a while, but it's going to work. As long as it doesn't say can't load or can't attach, it's going to be fine. So down here, this is where we actually get into manipulating our data. So in order to manipulate the data, using these packages, we're going to have to save it as a data frame instead of just a data table. And so to do that, you just do this command as data frame, and then you're going to put whatever you want to save as a data frame. And for simplicity, we're just going to call that my data so we don't have to type out as data frame every time. And then you can see up here, we've got a new data table called my data. Again, this is just a little warning message because I'm not using an up-to-date version of these packages, but it worked, so we're good. All right, so now we can find the mean of just one variable. So we just do mean, and then this time we input my data, the data set that we want, the $sign, so basically telling it, look in this data table in this specific column or this specific variable within that data table. So the $sign is just indicating this column. So we'll do column, and then the column is called eruptions. And so we'll run that, and there is the mean or the average eruption time. We can also specify it by saying my data brackets, the data within my data, the first column, and then is numeric. So we want to remind R that we are considering these numbers as numbers and not as objects. So you can run that, and boom, we get the same answer. You can also do this with other simple statistics. So min, you want to know the minimum value, or max, you want to know the maximum value. Median, you want to know the median. So we'll go ahead and run those. There's our 4 values, min, max, and median of these different columns, right? We've specified the min of waiting, the max of eruptions, the median of eruptions. And we can do all the column means. So we can find the means of all the columns with col means. And then you specify my data, and then you specify that you're applying it to all of my data for all the columns, and then specifying that it's numeric. You can do the same thing for rows. So if we run that, there we go. We've got the means for the 2 columns. Rows, we can do the same thing. And this is one of those situations where capitalization matters. This is lowercase all letters except for M here. We can also arrange the data or sort the data by specific variables. So we can do that with arrange, then specify the data set, and then specify the data that you want to sort by. So when we run that, we're going to see everything ordered from smallest to largest of our eruptions. If we wanted to know the waiting times, if we wanted to sort it by the waiting times, we would just put waiting up here. We can also pull out columns from our data set and save those as a separate data set using this select. So select is basically just saying select this part of the data set. So we can make a new data set called my eruptions, which is taking our 275 observations, but just that eruptions variable. We can also filter. So let's say we're only interested in large eruptions. So we could do filter my data eruptions are greater than 2. And then we can go ahead and it's going to show all of the values from my data that have eruption times greater than 2 minutes. We can make this a new data set if we want. There we go. We see my new data up here, and only 217 of those have times that are longer than 2 minutes. We can rename columns within the data sets. Let's say we're taking this new data set and we want to call the variable long eruptions instead of just eruptions. You use rename. So you do the command rename, specify the data set, and then specify the column name that you're changing. Oops, I didn't highlight all of that, so I would get an error message. There we go. We've got long eruptions now instead of just eruptions. Mutate. We can add columns using mutate. So we are mutating the data of my data. We're creating a new column called total time, and that's going to equal eruptions plus waiting. So we can mutate and see how that shows up there. There's our 3rd column. We can also create a new column, another mutate, a way we can mutate it by making a column yes or no if it's a long eruption. So we can just do mutate my data, the long eruption column, and then we can do an if else command. So if this first thing in the parentheses is true, put the second thing in the parentheses. If it's not true, put this 3rd thing in the parentheses. So basically we're saying create a new column called long eruption. If eruption time is greater than 3, put yes. If it's less, put no. And so we'll end up with a 3rd column here that says yes for longer eruptions, no for shorter eruptions. Whew. Okay, so let's get to plotting. That's what we all came here for, right? Plots. Okay, so we are going to basically, I'm actually going to just skip this step. Essentially what I'm doing here is just generating a new data frame by making a sequence from 1 to 1,000 by 2. So the data variable or the X variable is going to be 2, 4, 6, 8. And then the Y variable is just going to be a linear function. So Y equals 2 times variable 1 plus 3. So we're just going to create this new data frame real quick here so we can get to using it. There's our new data frame. Starting with 1, we're every 2. So 1, 3, 5, 7, 9. I said 2, 4, 6, 8, but I specified that I started with 1. All right, so now we are going to use the ggplot package. So that, again, you would go tools, install, ggplot will probably show up, ggplot2, there it is. I'm not going to install it because it gets confused if you install something you've already installed. Library, ggplot2, telling R that I'm going to use commands from this package. And then we're going to create our first plot. So what we do is we do plot. We can create a plot just like we create a list or an object. And then anytime we type plot or whatever we've named our plot, it's going to show up. So here we go. We've got plot equals. ggplot is the command that says make a plot or make a graph. Then the first thing we have to specify is what data set we're using. And then we specify the aesthetics. And this is basically how the plot looks. And by aesthetics, ggplot means what's on the x-axis and what's on the y-axis. So you do aesthetics, input is x equals whatever variable from that data set that you want to be the x variable, y equals the y variable. And because this is a linear function, we're going to specify that we want a line. So we are going to go ahead and write the command to make this plot, and then we're going to call the plot so we can actually see it. If we don't put plot at the end here, we're not going to be able to see it when we run that code. Uh-oh, what did I do? Oh, I forgot to load the library. There we go. And there's our plot. Yay, we made our first plot. All right, let's make some more complicated plots. All right, so I'm going to input some of my data from some of my work as a paleontologist. So this is going to be some geochemistry data of fossils. So I'm going to go ahead and just run this code chunk. If you want to input data from a file, you can do this code CSV, read.csv. So you save your data as a CSV file in the same folder on your computer where you have the R project. When we first opened it, we said new project. You save it in that same folder. And then you can just do read CSV to pull that data. And I've saved that new data as a new data set called paleo data, because that's my paleontology data. And there's the data. So it's just the chemistry associated with different fossils. And so I take a bit of the fossil, run it through a machine, and it's going to tell me some values associated with the chemistry. We're just plotting this data to see how to make plots. So don't worry too much about the exact numbers and what they mean. But we have data from different sites, and we have data from different animals, and then we've got some carbon data and some oxygen data. So if we wanted to plot this, here's what we're going to do. We're going to make a new plot, plot 2, and we are going to, again, use that ggplot data, saying we're going to make a plot with the data, specify the data set. So I'm specifying paleo data, aesthetics, x equals carbon, y equals oxygen. And these names are from the column names in the Excel or in the CSV file. So whatever you want to call those variables, we can actually open up this CSV file and view file. It's going to show up right up here. And so these are the columns: site, animal, carbon, oxygen. All right, so where were we? Down here. And then I want to create a scatter plot. And so I'm going to use this command geom point. So geom is basically the geometry of the plot. And then there's a lot of different options for what types of geometry we have. We can have geom point, we can have geom line, we can have geom box plot. And so the way to figure that out is if you want to know what options you have for different commands, you do a question mark, and then you type in that command. So I'm going to see what our options for ggplot2 are. Oh, why'd that not go? There we go. And so then this is going to show you all of, oh no, this is just showing you the information about who made this package. Oh, because the command is just ggplot, not ggplot2. So we're going to do ggplot. Run this. There we go. Now we're going to get all of the arguments. So we are going to go down here, and there's all of these different arguments that you can have, your data, your mapping, and then we can scroll down. We can see all these different examples, geom point. They must have changed this, because usually what happens if we just do question mark geom? Here we go. Now we've got all of our options. Geom ab line, geom area, geom bar, and you can query. So do question mark any of these, and it's going to tell you what that command will give you. And then it'll show you an example as well. All right, so back to what we're doing. The way that you can change the color, so right here when we did this, it had that gray background. Let's say we don't like that. We can do theme. So theme is a command to just change the appearance of any component of the plot. So theme underscore BW, that's black and white, but there's a lot of different options. You can do theme dark, theme classic. And any text that you have in these code chunk boxes that's not part of your code, just put a hashtag in front of it. And that's telling R that when you run this code, don't run the text with the hashtag because that's not a command. So I have a couple different alternatives. And if I wanted to switch, I could just hashtag this out. Oops, not plus sign, hashtag, and unhashtag this. And so, hang on, it's not liking having this in front. So I'm just going to move it. There we go. You see it turn black, and that means that it's going to run it as code. You can also change the X and Y labels on the axes by using XLab and YLab. And in this case, we're saying an expression because I want it to say this text, but you can have it say numbers, whatever. You can also just come down here, do question mark X lab, enter, and then over here, it's going to show you all of your different options. Yes, you can give it subtitles, you can give it captions, all this stuff, and then some examples. We can give the plot itself a title by saying here, GG title, and then we can do theme. So GG title plus theme. In theme, in that case, is going to change the GG title as long as we keep it inside the, or keep it with the plus sign, adding it to this command. You can add a horizontal line on your plot here by doing geom_h line and then specifying the y-intercept. You can change the line type and the color of it. Same with a vertical line. If you want to write some text on your plot, you can come here and just do annotate and then put whatever you want and then specify X and Y coordinates where you want it. Same with segments. So you can put geom segment, that's just a line segment. You can add arrow if you want it to be an arrow instead of just a line. And then you can again change the theme of all of these different things, the axis text. So once you do theme, you can change the x-axis text. You can make it bold, blue, change the size, change the angle. Same with the Y text and the numbers on the axis. You can change here. I'll just show you. We're going to run this. Can't add theme dark. Why not? There we go. Why is this still not? Oh, because I just have theme dark and I don't have the parentheses. The parentheses are always part of the command, whether or not the command requires an input. There we go. So here we've changed the theme to dark. There's our data, all these points. We've changed the title. We've made it red. We've put in these horizontal and vertical lines, all this nice stuff. We put in an arrow, and that's all with these commands up here. The other thing that we can do, we're gonna move pretty quick. I know we are running short on time. So if you have to leave, feel free to head out. We are recording the webinar. So if you need to come back at a later date, you can check it out later. I will also send this R Markdown file plus the slides out to you. So you'll get that in your email. So you can always revisit this code whenever you need to. But here, what we are going to do is we're going to add another way of determining what variables we're plotting. So here we just have our X and Y coordinates, but each of these points also comes from a different animal and a different location where that fossil was collected, a different site. So we can color code the data by some of these other variables. And so here we are color coding it by site. And we're putting factor here to recognize that site 1 is a discrete site and that we're not going to have 1.1, 1.2, it's just going to be 1. And so here in our plot down below, all of the different data points now are different colors based on what site they're collected from. And again, in aesthetics, that was color equals and then whichever variable. You can also do the same thing in terms of making different sizes or different shapes for the data points. And so in this case, we've added two different things. We have added, so we've got our color there, and then this time we have shape. So shape is by animal. So each different animal is going to have a differently shaped data point, and we're going to get a nice little legend over here. So all the circles are points from crocodiles, triangles are points from dinosaurs, and same for fish and snails. And then the size of the data point corresponds to some value. And so in this case, because we already had carbon and oxygen separate, we did a mutate data. We added a column for total being carbon plus oxygen. And then we are coding the size of the data point based on the total. So you can see that showing up in the legend as well. All of the data are similar in value, all the totals, and so there's not a big difference in size, but you can see this plus sign down here is pretty small, and these squares and circles up here are pretty large. All right, so now I told you I'd show you how to make it in a grid. So if you want to grid it out with kind of one row with different items in it, with different grids in it horizontally, you would do this command facet wrap. So you would do after your aesthetics and after the type of plot, you would do plus facet wrap, and then you would do the little tilde signal to tell R which variable you want it to be split up by. So in this case, we're splitting it up by animal. And then you would indicate the number of columns, and call equals however many columns. Then you can do the same thing for rows. Did I not have, oh, I didn't have a separate chunk for that. So here, we're just gonna switch it out. We're gonna hashtag this right here. Oops, not plus, I did that again. And in this case, we're gonna do a facet grid, which is gonna give us, what did I do here? What errors are we getting? Okay, so it's not liking new paleo data. Oh, because I didn't run this up here. So the command to specify what the new paleo data set was in that previous code chunk. And because I didn't actually run it, I just scrolled down here. Hang on one moment, sorry, I'm getting a phone call. Scam. Okay, so because I didn't actually run that code when we looked at it, that's why it didn't work. But now we will run it again. And there it is. That's the same. Why didn't it do the other one? Let's just go ahead and delete this here. It is not liking something. All right, what is the problem? See, this is a great example of what actually happens. But a lot of what you do is just troubleshooting. All right, it is still not liking something. Why? We'll run just that, and now we'll run this whole thing. All right, let's try just typing it out. There we go. That's the problem. I deleted the wrong command. So now we have it in this facet wrap, whereas the grid was just the columns. So you can play around with that. You can add columns, you can add rows, do whatever you need to make your data the way you want it. To make a bar plot, you just do geom bar, and then you specify the color, or you can specify the width of some of these, and then do the rest of the plot however you'd like it. You can do a pie chart, and that is basically just taking your bar plot and then doing a polar coordinate shift to it, which is this command _polar. You can do a box plot or a stem and whisker plot, whatever you call that. They're the same thing, different names. And then here is our command box plot to make that plot. You can do a histogram plot, just do geom _histogram, and there's your histogram. Lots of different options. Okay, so I know we are pretty much out of time. So if you all would like to stay on and see the model for COVID-19 and how to build a model in R, I'm happy to keep talking here, but I also understand that you probably have a lot of things to do today, and so you do not have to stay at all. if everyone, wants to leave, I'm also happy to let everyone go and end the webinar now. So if anyone in the chat would like to kind of give an opinion on that, what they'd like to see, if they want to stick around and see the model, or if they prefer not to, just put it in the chat. Let me know what you want to do. All right, let's see. We've got 1 vote to see the model. All right, why don't we did have 1 vote to see the model, so I'm going to keep going. If you need to leave, thank you so much for joining us today. Please feel free to email me. Again, it's just victoria.crystal@colorado.edu. That's my email. I'm happy to answer questions, help you troubleshoot if you need. Yeah, so if you have to leave, thanks for joining, and this will be available for you to rewatch later on. All right, so COVID-19 model. Actually, let's switch back to our PowerPoint here. What is a model? A model is basically something that uses logic to organize things, whether that's a situation or event or processes, into different components and how they are related to each other. And so mathematically, what that translates to is each aspect of the model, each component, is basically going to be something that we are defining, just like we defined data sets or lists or objects. We are going to define a part of this system. And then that component is going to have its own set of parameters. So what it equals, and then also inputs and outputs. So what is going into that portion of the system and what's coming out. And this is how we would draw this out. This is what we would call a box model, where each component is a box with outputs, an arrow away from it, or inputs, an arrow to it. So an example of how I use this in my research is sometimes I will create a mathematical model of an ecosystem. So let's say I'm studying dinosaurs in southern Utah, and I'm interested in how everything in the ecosystem is interconnected. And so I'll create a model. So I'll break down that ecosystem, that big system that we're trying to model, into different components. Components being the sun, the atmosphere, the soil, the plants in that ecosystem, the herbivores, carnivores, detritivores, and then I'll figure out how is everything interconnected. So the sun is giving energy to the plants are taking that in, photosynthesizing, then those herbivores come along and they eat the plants, so they're taking in the plant material. But they're also taking in air from the atmosphere, they're breathing just like we breathe, all herbivores and carnivores, all animals will do that. They're also drinking water. Plants are putting and taking nutrients and water from the soil. And so all of these are interconnected, and we can represent them by equations, right? The sun puts X amount. Oh yes, in the chat too, microorganisms too. Yes, so important to ecosystems. Ecosystems could not function without microorganisms. Yes, we've got our detritivores that are decomposing all of that plant matter, and also any other organic matter that gets into the soil. And so we represent these with equations. So we can say X amount of energy is being transmitted from the sun to the surface of the earth. Within this ecosystem, we have X amount of plant biomass. So how many plants, how much plant material do we have? And we can do that for all of these different components. And so for our COVID-19 example, this is what we are going to do. And before we get into it, I do want to say none of this is based on real COVID-19 data. So when we're talking about fatalities or people being hospitalized, it's just hypothetically based on a population of 10,000 people. So it's just hypothetical. It's not based on any real population. It's just saying if we had 10,000 people and COVID-19 was being transmitted from person to person in that scenario, what would this look like based on what we know of how severe symptoms can be and of how COVID-19 transmits from one person to another. So the only aspect of real data is that we know the value, it's called the R value, of if one person is sick and they go about their daily lives as usual, how many other people are they going to get sick based on how infectious COVID is. So that's a number. I believe right now that number is 2.5. So for every one person who goes about their daily routine, 2.5 other people are going to get COVID from them. So that's what we're talking about here. No real individuals, all hypothetical, just based on epidemiology theory. So the components that we have are susceptible individuals, and we call this component S, or compartment S. Compartment, component, same thing, different word, same meaning. So susceptible individuals. So how many people can potentially get sick from COVID? And we're going to start off with our hypothetical population of 10,000 people. 10,000 people are available to get sick. E is exposed. So someone who has been exposed to COVID, to someone who is infected, and they are infectious. They have the virus, they can give it to someone else, but they're not symptomatic. They don't feel sick, they don't look sick, they can't tell they're sick, but they can still get other people sick. Then we have the infected, the I compartment. So that's someone who has gotten sick, they're exposed, they've gotten sick, they are infected, they can infect other people, and now they are starting to feel sick. Now they have a fever and they're having trouble breathing. Then we have Q, which is the number of people that have quarantined. So people who are infectious, they can get other people sick, and they know they're sick, but they're staying home. They're not going to work, they're not going to the store, they're not doing their daily stuff, they're staying home, staying in bed. Then we've got H, which is the component of people who require hospitalization. So people who would normally be hospitalized if there was capacity available in the hospital. The problem with COVID is that we have so many people that are requiring hospitalization that we can't get all, like there's too many people and not enough hospital beds. There's not enough capacity. Then we've got R, which is the recovered component. So someone who was sick and now they've recovered, they're not sick anymore, they can't get sick again. New data is suggesting, since this model was made in March, that potentially those people could get sick again after a certain amount of time, but we don't know that yet, and that's not part of the model. And then finally, F would be a COVID fatality. And so let's take a look at the model. So before we get into the model, I did put this text here. So for those of you who aren't still here, not that you know that I'm telling you this, but you'll see it when you look at the materials. This is all the information. So I didn't make this model. I got this from a health science data blog. So this model was made by Tim Churches, and he uses a package called EpiModel, which is made from the Emory University School of Public Health, and that is commands that specifically model epidemiology. So how viruses are transmitted from person to person within a society. That's what epidemiology is, the study of viruses. And so this is a specific code that has functions that are associated with transmission from one person to another. So none of this is real data, says that right there. I also am not an epidemiologist, and so I don't necessarily know all of the work that went into developing this model. I just do the data side of it where I know how to work the model. So there's a lot of packages that are required for this model. There's also some other files that are stored on Tim's GitHub website, which is kind of like social media, but for people who do a lot of coding. So you can store information on your GitHub and then just write the R code to cite this thing that's online. And that also allows Tim to update it. And so instead of you having to download something every time Tim updates this package, it just will automatically pull from that website. So we're not going to go through this code line by line by line because it is very, very long. But basically, we have to run all of these packages and all of these source files. So I'm going to go ahead and run that. This is probably going to take a minute or two. Oh, no, it's going pretty fast. So there we go. It's loaded everything. You notice up in our environment, we've had a lot of new objects, new values pop up. All right, and then we get some error message. Well, it's not really an error message because everything seems to have worked. These conflicts are just because my packages aren't all up to date. But if your packages are up to date, recently downloaded, you won't get any of this red text. And if you do, as long as it doesn't say error or something didn't work, then you're good to go to keep going. So this is the actual model that we're putting together. And so basically this is all the math that says we have this component. This component has this value and it has this input and this output. Oh, I didn't show that part of my PowerPoint slide. So this is what we're modeling here. So this is our susceptible population. And you'll notice that we can have, our susceptible population can have an input from our exposed and infected population, an input from our infected and infectious population, so they can get sick, or they can also, they can quarantine, or these quarantine people can get them sick if they're not quarantining or if they're done quarantining. So there's a relationship between susceptible to all of these. Someone who is susceptible can also become exposed and vice versa. Someone who is exposed, vice versa, and then also they can become infectious. If they are infectious, they can quarantine themselves. And we can input all of these. Like we can say what proportion of the population is quarantining. And then based on that, it goes back to how many people are susceptible if you have these infected and infectious people who are staying home. Then if someone is quarantining or if they're infected and infectious, they can go to the hospital or they can recover. So arrow all the way here, go to the hospital or recover. And then someone in the hospital can become a fatality or they can recover too. And then recovered people do not go back to this susceptible category because in this model, we're saying that for the time being, you can't become infected again. And so now let's actually take a look at this model. So here's just all of the commands that go into writing the math essentially. But what we're going to focus on here is this set of parameters, this set of commands that's specifying the number that we're starting off with. So we are going to start off with 9,997 people who are healthy and in the population, but they are susceptible. And we're going to start off with 3 infected people. And then here are the rates for how these things change over time. And the ones that we are going to focus on here is the quarantine rate. So what we are going to say here is 1 in 30 people who are sick and are experiencing symptoms so they know they're sick are staying home. That's not a lot of people, right? 1 in 30 people who are sick and know they're sick are staying home. The rest of those 29 people are going to work, going to the store as usual. And that's how this virus spreads. People who are sick still going out into public, interacting with people and getting those people sick. So that's going to be what we focus on for this model. And then the rest of it is basically just saying we're going to run this model for a simulation. I believe we're doing 100 days. So if this continues for 100 days, only 1 in 30 of the people that get sick and know they're sick stay home. How fast are we going to have the number of people that are sick, that are susceptible, that are in the hospital, that are fatalities? How fast are those numbers going to increase? So we are going to go ahead and run this. This is going to take a while because we're inputting all of these different parameters. So we're going to see this turny wheel for a little while. So what we're going to do is we're going to run this, and this is kind of just going to spit out, so to speak, the raw data. And then we're going to take our cool ggplot tools and we're going to make that data look a little bit easier to interpret. So once this loads, you'll see what that raw data looks like. It's a lot. I mean, look at all these lines of code. It's going to take it a little while. And plus, anytime that you tell R that you want to run a simulation. So a simulation is, inputting all these parameters and then kind of saying, all right, what's going to happen when these components interact with each other? Anytime you tell it to make those components interact, it's going to take a little while for all of that code to run. Oh, there we go. It's almost done. All right, so there's our raw data. It's just kind of a bunch of histograms, and that's hard to interpret. And so what we're going to do is we're going to take the results of this simulation, and we are going to use some of our wonderful ggplots, ggplot tools here. So you can see we've used ggplot. There's something that looks familiar, aesthetics, x equals time, y equals count, so the number of people. And then color equals the compartment. Oh, one thing to note, The people who developed R, originally they are, I think they're British. They must be British. They speak British English. So color can also be spelled with a U. I believe it will still work if it's not spelled with a U, but it does have those differences between British English and American English built in there. All right, so this is what we get. This is our simulation. So we've prettied it up. We've used this theme dark, and we've split the colors based on the components. So what we have here, like we said, we told the x-axis that it was days since the beginning of the epidemic, or the pandemic in this case. So 0 is day 0, and 100 is after 100 days. So on day 0, we had 9,997 healthy people, and we had 3 sick people. So that's this red line. So that's people that have the virus, and they know they have the virus, and they can get other people sick. And so what we see is this huge spike in red, right? It goes up real fast, makes a really big spike. That's a lot of people getting sick. We don't want a lot of people getting sick. We don't want a lot of people making other people sick. And so this is the curve that we talk about when we say flatten the curve. We want to flatten that curve. We want to make that much smaller so we don't have a lot of people in our population that are getting sick. Now, one thing to note is that we do have this black line is our case fatality. So while we have a lot of infected people, we do have lower fatalities. Not all 3,000 of these people that got infected died, which is great. Of course, we don't want people to die. So it's great that that case fatality line is really low. But the problem is, and this is not part of the model, a lot of the people in this population of this red curve, they end up with what we call morbidities, which are consequences of getting sick. It's not mortality, they didn't die, but there's things that are wrong potentially permanently, or at least in the long term, with their lungs. And so not only do we want this line to be really low so people don't die, but we want the red line to be really low so people don't get sick and people don't potentially have permanent lung damage from COVID. So that's why we want this curve to flatten. So let's see how we can flatten it, how we can model a flattening out of it. So what we can do is we can increase this rate of people staying home. That's how we stop other people from getting sick. If you're sick, stay home and you won't get anyone else sick. So what we're going to do in our model is we are going to increase that from 1 in 30 people staying home to 1 in 2 people staying home. And we're going to specify that we make that change on day 15. So on day 15, someone says, all right, we've had enough. If you're sick, you better stay home. And so 1 in 2 people start staying home. So we're going to let it do its thing. And then here we go. I've built in our ggplot into this code chunk. And so it's going to take that raw data from the simulation and it's going to put it in that nice chart like we just saw. So we'll give it a minute here. Do we have, all right, maybe I won't run it from now on. Because I ran the code this afternoon to make sure it was all going to work, and you still see the plots showing up there from when I ran it earlier. So maybe the trick is don't run it. Oh no, I've got to run it again because each code chunk refers back to something else from the previous code chunk. And so if you haven't run that, it's going to get confused. All right, so here's our final output. So again, we've got our days since the beginning of the pandemic, and we've got the number of people that are sick. And we've just separated out. This top chart is our baseline, so that first scenario that we ran. And then this second one is when people start, 1 in 2 people start self-isolating instead of 1 in 30. And so what we end up with is, yay, a big reduction in that red line. We don't have a lot of people getting sick anymore. That's good. We have flattened the curve in this situation. But we still have, you know, a kind of significant looking orange spike here, which is our infected and asymptomatic people. So that's someone who's sick and they can get other people sick, but they don't know they're sick. They feel fine. And typically that happens first, and then you feel fine, and then you get COVID, but you've already interacted with a bunch of people that you could have gotten sick. And so what we want to do is we want to further try and reduce this orange line. So we are going to make a couple more changes. So we are going to do some more models. So we are going to go back to that first scenario with our infectious people. Oh, wait, we already did it. Didn't we do this back in the low level? Oh, right. But this time we're adding social distancing. Sorry. This time we're going to add some social distancing. So not only are we having people who are sick stay home, but we are going to go back to that lower line just to compare. So we are only having 1 in 30 people stay home if they're sick, but we're going to start social distancing. And basically what the social distancing component says is if these people aren't in close enough contact, then they're not going to go from susceptible to infected or susceptible to exposed. And so we are basically just inputting into the data that people are staying farther apart. And so even though you're going to work, you're staying far away from people so that you're not getting them sick. And so we are going to run that simulation. Actually, let's just take a look at this. The other thing that you can do is if it's kind of small because it's just in this R Markdown, you can you can right click and then you can hit open image in new window, and this is going to open it. So this up here is our baseline simulation where we've got that really bad curve with a lot of people getting sick. This is the simulation, the second one that we ran, where we've got people, 1 in 2 people starting on day 15 are staying home. 1 in 2 people who know they're sick are staying home. So we've significantly flattened that red curve. This is our example where we go back to this original number of 1 in 30 people who know they're sick stay home. So a lot of people still going to work. We don't have a line for social distancing. That wasn't written into the model. If you want one, you could totally write one. Just specify, pick like SD for social distancing, and then you can just specify the parameters for it. So this scenario, we have 1 in 30 people who are sick and know they're sick staying home. So a lot of people still going to work. But when they're at work, they're social distancing. So they're not getting close enough to get someone sick. And as you can see, that does significantly reduce the red line from 3,000 people up here to less than 2,000 people up here getting sick. So that's good. That's flattened the curve, but we can do better. This is our scenario where we start social distancing at day 30. So we keep that 1 in 30 people that are sick staying home, but we wait 15 more days. So this starts social distancing at day 15. This starts social distancing at day 30. And as you can see, this brings us back up to over 3,000 people are getting sick again. And that's one of the things, and this is why you hear on the news sometimes, like 2 weeks from now, there's going to be a big spike. Or when the pandemic first started, people saying that even though there's not a lot of people sick, we need to start social distancing. And it's from data like this. So like Dr. Fauci runs models like this and basically says, okay, if we wait 15 more days, we are going to have almost 1,000 more cases than if we tell people to start social distancing now. And so it's just a way that scientists can model this and help inform the public. So when you hear scientists say stuff like this, it's based on mathematical models, and now we know how to do them. So that's what that's why I love R so much, because you can do so many cool things with it. And it seems almost like magic. Like, how do you know that? Like, how do you know that there's, it's going to make a difference of 15 days, making models, writing out equations, telling R to run these equations for X number of days. It's awesome. All right, and then finally, this last scenario here, kind of went on a tangent there. This is where we bring that number of people who are sick and know they're sick and stay home. We bring that back to 1 in 2 people. So half of the people that get sick are staying home. And then we are also starting social distancing at day 15. So people who are sick and know they're sick, half of those people are staying home, and everyone else in the society is social distancing. So even if you're in that half of the people that don't stay home, you're staying far enough away from people that you're not infecting anyone else. And look at this. Look how low our infection line is. Look how low our fatality line is. You can't even see it on here anymore. I don't even see the black line. It's so low. And so that's what a lot of these social distancing and mask wearing protocols are calling for. We don't have mask wearing in this yet, but that kind of goes along with social distancing. You're just preventing the germs from getting to someone else. And you could even write that into the model, right? Like specify like M mask wearing population or something, and then calculate, okay, so what would be an input? If someone wears a mask, the rate of them getting infected is, reduced by half or something. You can play with that. Check the scientific literature, see what it says for how that rate is actually reduced, and just play around with all these different components. So some of the text or some of the code for this model is a little bit complicated. So what you can do is click on this link to Tim's GitHub. Where was that? I didn't hyperlink it. You can also hyperlink it. Just write the code that says this is a hyperlink, so you don't have to copy paste it every time. But we're gonna have to copy paste it. All right, and then here is Tim's GitHub, and so there's the code, but you can go to his homepage, and you can see all of the different codes that he's written. He's got his R Markdown files right here, and so you can find. Oh, he's from Australia, so that's why we had color with the U. So this is his COVID information. So you can just play around and get all the information that you need. There's also in the resources of my PowerPoint, there's also some links. Let's see, there's his actual blog, not his GitHub page. And so that can also really help you if you've got questions on that. He troubleshoots some stuff on that blog. And then there's also all of these different references that you can use. There's a fun Pirates Guide to R, because it's R and pirates like to say R. There's some cool data visualization cheat sheets. And so all the commands that you need to make different plots. There's a data wrangling cheat sheet. So all the different codes that you need, like select, arrange. If say you forget how to sort by the numbers in a column, you can look on that data wrangling cheat sheet. So there's a lot of great information in this R webinar file, the HTML. I've actually put all of this. Is going to be a lot of scrolling. That's that faithful data set. I've got all of my slides here. Another thing you can do with R, you can plot different slides. So if you needed a slide to show up in a report you were writing, you could just do this. The code is right there for you. So it's all there together. This is going to be mailed out to you. And I know that we are way over time here. Thank you so much for sticking with me. Last time I did this webinar, I went over and I thought I was going so much faster this time, but apparently not. But I'm happy to take questions if you all have questions. Feel free to put them in the chat, use the Q&A, whatever you would like. If you got to go, head out. Thank you so much for coming here today. Reach out if you've got questions. Utilize those resources in the slides. They're going to be real helpful. I'm going to go ahead and stop sharing as well. That way I've got the second monitor over here where I've got the Q&A and the chat open. But I'll go ahead and put them over here. Thank you, everyone. I'm so glad that you were able to be here. You are welcome, everyone. Does anyone have questions? I don't know where my cat went. I think he went somewhere to take a nap. He'll do that. He'll come and he'll hang out and, you know, poke his head in the camera, say hi to everyone on Zoom, and then he'll go take a nap, and then he'll come back in. Oh yes, for the certificate, DoSpace will actually send you out that in an email after this program. All right, what does this say? Are there online? Oh, yes, there are. Let me see. I know there's a lot of biology specifics. Let me give it a quick Google. I only do a very tiny little bit of biology. Let's see, let's see. I don't know why that didn't type. Hang on. R for biology. Oh yes, sorry, I forgot that not everyone can see the questions. Let's see here. Here is a website, R for biologists. So I'm gonna go ahead and put this in the chat. All right, so there is R for biologists. Let's see what else I can find on a quick Google. I mean, that is just one of the most amazing things about R being open source, is that there's so many amazing resources out there. Here's one from the University of Cambridge. This looks like it's pretty good. Let's see. Oh no, this is just a course description. Just kidding. Looked like it was gonna be really good. Let's see here. Let's try a different one. Oh, here's a cool YouTube video. I bet this will be useful. I'll go ahead and put this in the chat. All right, let's see here. Yeah, so the great thing about R is that you can just Google and you can find, oh, here, this is actually from the creators of R. So this is, this is put out by the creators of R. So here, this will probably be a good one. This looks like it's a whole book or a chapter from a book or something. Yeah, this will be good. Oh yeah, it's going through all the details. Yeah, so check out some of those resources. And then other than that, you can just do your own Google, and most, 90% of what pops up is gonna be really, really great and really useful. Let's see. Question in the Q&A. Yes, there's a certificate, so it's just going to be sent out to you via email from DoSpace after this. And then this question, oh, you are very welcome, Ray. Ray just said thanks in the Q&A. Oh, and in the chat too. There we go. I see that now. Other questions? That's a good question. So the question in the chat is, you mentioned that the learning curve is steep. Approximately how long does it take a total newbie to learn R to achieve proficiency? It kind of depends on how much time you have and how much you need to use R. So when I was first learning, I was just kind of casually, like every 2 or 3 weeks, I'd go onto R and I'd try and do something. And that was kind of frustrating because 2 to 3 weeks of not using something, you kind of forget. And so that, if I had done that, it would have taken me a very, very long time to learn R. But then when I needed a project, I had 2 weeks to do a project. I have 2 or 3 weeks. And so I sat down and I put in as much time as it took to get it done. So I would say it was a good, like, let's see, probably a solid week of like 6 to 8 hour days, like, you know, sitting there doing that all day at work, and really just tackling R. And it's a lot of kind of what I call copy paste coding, where I know what I want to do with it and I Google, how do you make a box plot in R? And then I read what it says on Google, and most often people will post their code, and I'll just copy paste my code into a code chunk and run it. And so with copy paste coding, you learn like pretty quick, because once you do something, you're like, okay, I've got the code for that, so I know how to do it again. And so I would say like anywhere from a couple hours, depending on, you know, the scope of your project, to, you know, work week. And for some things, it's a lot easier, like the ggplot stuff that kind of builds on itself. So it's like you have, you know, what's an example? You know, X labels, and then you can change the angle of the X labels. You can change what the text says. You can change the size. And so it's all very similar. It's all size equals, and then you put it in. Color equals, and then you put it in. And so that you can pick up pretty quick. Stuff like Tim's model, that's really challenging. I still don't even understand the entirety of Tim's model. I don't think I could build that model on my own, because I rely on Tim, who has probably been doing R for years and years longer than I have. And so it just kind of really depends on how much time you have to devote. I don't really make a lot of models anymore. And so I don't really devote much time to trying to work on the models, but if I did, it would probably be like a good work week or 2 work weeks or something, to get to Tim's level or something. It's just the time. So that was a very long answer to your question. But hopefully that answers it. There's another question in the chat here. Do I have another webinar? I'm not doing another R webinar. I am doing a webinar about how to use Google Earth. So I'm going to do that one. Look at my calendar here, February 25th. I'm going to do a webinar all about how to use Google Earth, kind of all the really awesome tools, from like just finding your house on Google Earth to making like a virtual vacation, or like a virtual map to show off a vacation you went on or something. So that'll be February 25th at 6:30 p.m. But as of right now, I don't have any other R ones. Let's see. Oh, questions from Facebook. Don't have. Oh, okay. Cool. Let's see. Yes, the Google Earth webinar is going to be through DoSpace. So you should be able to find it on their website. It's on the calendar. I just sent in the description a couple days ago, so that should be appearing on the website at DoSpace, on DoSpace's website soon. But yeah, it's through DoSpace. All right. Any last questions? I feel bad taking so much of your time. So if there's no questions, I'll give it like 1 more minute for questions. But otherwise, we can all sign off. Thank you again to everyone who joined from all over the world. I love that with technology, I'm able to talk to you all that are in the Philippines, even though there's a big ocean between us. Yeah, thank you everyone for joining. All right, it doesn't seem like there's any more questions, a lot of thank yous. So thank you all, and I hope you have a great rest of your day, whether it's just starting, if it's in the morning or if it's at the evening. Yeah, thank you so much and have a great day and a great, happy new year, even though it's almost the end of January. So bye.